Okay, real quick, I just wanted to say that that table of Laplace information, it will be linked in the description. So don't worry about trying to copy it all down. Okay, so we're going to try to solve these two differential equations using Laplace's method. And yeah, it would be 100% easier to use any other method than what we're going to do, but these are two good examples to start off for just learning how to use Laplace transformations to solve the ease. So for number 12, we'll do this completely in blue. So what you do is you say the Laplace of the differential equation. So that means the left hand and the right hand side, right? So everything in here and on the side is in here. And well, since the Laplace and its linear property, you can say Laplace of y prime plus the Laplace of, we'll put the minus y here. So usually you put the coefficients on the outside of the Laplace to make it easier. And then Laplace of 0 is just 0. So this tells you a lot already. Well, you know that Laplace transformation of y prime, it goes to what? It turns into s y s minus y of 0. So this big Y, it's a different variable. For now, it's just big Y. We don't really, it's just a variable, right? But it's a different variable from Y. And these parentheses here, it's not saying it's multiplied, it's meaning it's a function of. Okay. So SYS just kind of stays. Minus YO, that's our initial condition, so minus 1. Okay. Next thing we got to do is do the Laplace of negative 1 y, which is just negative 1 big Y. That's all it is. Like, that's it. If it's just a regular Y, no derivative, just we take the Laplace of it, turns into this. Okay. So let's make a note of that real quick. Laplace of y is equal to big Y. Well then, what does that mean? Well, it means that we take the inverse Laplace of big Y, we get Y. So this will be useful later. We're going to see that this will eventually lead us to our solution. But first, let's just group these together because I broke them up just to make it easier for you to see. But let's bring them back and put them in one big equation. So this becomes s y minus 1, and then it was plus this, right? S, yeah, this one, this over here, replace that, and this over here is replacing that. So minus 1. It's all equals 0. Okay, maybe we can write this as, we'll put the 1 on the other side, so equals to 1. And then let's put the y, the big y's, let's factor it out. So it'll be big Y, and then there's a s, and there's a minus 1 here, so it'll be s minus 1. Okay, and then we could do one more step, because we want this big Y by itself. Or you can call it a pitchfork if you want. Just 1 over s minus 1. And then this is the part where you would use this fact to get your answer. Now you're like, what the fuck is this? Okay, now I'm going to drag into the shot. This is why people like using Laplace's method for harder equations usually, because nearly every single situation is solved. So what do we have here? We have a 1 over s minus 1. So that's going to look something like, where is it? 1 divided by s minus 1, where a is 1, 1 is a, right? So it's going to be, so e to the at. In our case, it'll be what? It'll become, so we take the inverse Laplace of big Y. And in our case, it's just going to be e to the t. And yeah, let's check if we got, yeah, e to the t. Okay. And that is equal to y. So that's our answer, actually, just right there. Okay. And real quick, I noticed that there's an x here. So I guess they're saying y is a function of x, and I said y is a function of t. It's t and x. It's just dummy variables, right? There's no difference. For the second one, I'll use x, though, for my final dummy variable then. Okay, everything for number 2, for number 13, we'll do in black. So I'm going to jump a step here and immediately use these, right? So, and since I already have these and these are the same thing, right? I already know it's going to be of this form right here. So it's going to be sy minus 1 minus 1 big Y is equal to the Laplace of what? E to the x. So the difference is that this one has a Laplace of e to the x instead of Laplace of 0 on the right hand side. So then real quick, let's just ask a question. What is the Laplace of e to the x equal to? Well, we want it to be some function of s, right? So some function of s. Now, what is that function of s? We kind of don't know. Well, we do know it's going to be this, right? But let me just show you the table again so you believe me. So in our case, we had, wait, let me show you. So we had e to the x. Oh. So if we had a e to the x, we'll go here, right? So this is like just saying these are the formulas to use. If you have this, go to that. If you have this, go to that, right? It's the same situation. That's why I wanted to do this problem because it kind of shows you the ins and outs. So specifically for us, it's going to be 1 over s minus 1. That's specifically for us, okay? This is our answer. Okay, so then we could say the same thing where we go y s minus 1. That's because we have the same left-hand side. That's why we can use the same left-hand side. And then we could also still have that 1 on the side, except we have this thing here. So it's plus 1 s minus 1. And if you're confused about the shortcut I did real quick, I'll just do it from scratch here just to show you. Okay, so our dE was like this, right? It's s y minus 1 minus big Y is equal to, and this thing is equal to that, right? 1 s minus 1. So all I did is I used the shortcut, and you can see that these two things here are exactly equal. It's just a different way of writing it. Okay. And if we want big Y by itself, this is, so you put the 1 on the other side, so 1 plus that, as you can see, it'll be 1 plus that, right? So 1 plus 1 over s minus 1. And 1 second. Jumped a little too far ahead. We had big Y, and it'd be s minus 1. Okay. So we're back to where we are at. Okay. And now we go one more step, and we want big Y by itself. Now we can do that thing. And it's going to be 1 over, so I'm going to just divide everything in here by 1 divided by s minus 1. So it's going to be 1 divided by s minus 1 plus 1 over s minus 1 squared. Okay, so here we are. Look at that right here. See that? Same thing. So we can already jump to the answer. That's e to the t. So let's write L inverse of y is equal to y, right? Because that's our fact. But y is equal to y1 plus y2. You kind of remember how we like had that thing for like variation of parameters and like all that type of stuff, how we can have, you know, these little family of solutions, these little mini y's in our big Y. Okay, well, specifically, our y1 is equal to the inverse Laplace of 1 over s minus 1, which we know to be, in this case, we said e to the t, but like I said, just a dummy variable here. I'll agree with the book. We'll go e to the x. Okay, and then y2, what do we got here? It's going to be inverse Laplace of 1 over s minus 1 squared. And instead of doing partial fraction decomposition, since every single version of this is known, I'm sure we can find it here. Let's see. Looks something like this one right here, right? We had a n plus 1. So our n was just 1. So and it'll be 1 factorial, which is 1. So we can use this formula. So our formula should look something like this. I mean, our answer should look something like this for y2. Okay, let's go back. So let's just break it down. I'll rewrite the formula real quick. N factorial s minus a n plus 1 is equal to, and sorry about the bad spacing right here, is equal to t. Instead of saying t again, I'll say x. X then e to the ax, I believe. Let's check. Yeah. Okay. So in our case, a is equal to what? A is equal to 1, and n is equal to 1, right? Because there's a 2 here, but it's n plus 1. So n has to equal 1. So then we know that y2 is going to be something like this, but we just got to fill in the gaps here. So x to the 1 power, because n is 1 for us, and e to the what? E to the x. Okay, so then y is equal to what? Y is equal to this plus this. Okay, so e to the x plus x e to the x. If you want to be fancy, you can write it like e to the x 1 plus x. There we go. So that's your answer. And as you can see, Laplace's method, it's kind of like this idea of get a differential equation, turn it into an algebra equation. When it's an algebra equation, look at your table, pray that something sticks out, right? Pray that something sticks out. Or maybe you got to be a little creative to make it look like these. And then you go back, and then if it doesn't look like it, you got to break it up a little bit more, like how we did. And then you take the inverses at the end when you want to get to your final answer, when you want to get your boxed solution, what y is actually equal to. This is the solution to the differential equation. Okay.
Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up the algorithm.